Hi, let's take a look at the opamp. Short for operational amplifier, usually comes in a little chip like this. This is the package, 8-pin package. Inside of this thing is the opamp, usually drawn as a triangle like this. One output, two inputs. The general equation is that the output is equal to some kind of gain times the positive input, this one, minus the negative input, this one. So it takes the difference, the signals on these inputs, boosts it up and gives you the output. So for example, let's do 100 millivolts, 0. So let's just tie this to ground. So 100 millivolts minus 0, amplified by some gain. It's a very high number. The ideal op-amp has the gain to be infinite, but we can't use infinity. Let's just do 10,000. So that's going to be 100 millivolts times 10,000, that's 1,000 volts, right? Something like that. But you get the idea. So can this amplifier amplify to 1,000 volts? No, you will have power pins here. Could be this one or this one. And here you'll put maybe 15 volts. Here you'll put maybe negative 15 volts. And now the output can fluctuate between 15 volts and negative 15 volts. So you can amplify anything in between. So in this example, we do 100 millivolts. We got that to be 10,000 volts, which means that it's just going to saturate. It's not going to reach the 1,000 volts. It's going to hit the 15 volt ceiling. This is going to be your ceiling. So let me find the pinout for a op-amp. Here we go. So here's the VCC plus VCC supply. So let's tie that to 15 volts. Our negative, let's tie that to negative 15 volts. And here are our inputs. And we put 100 millivolts here. We don't have to worry about the offset. We don't have to worry about the no connection. We don't have to worry about that. This is our output. And the inverting input, we put that to ground as well. Okay, so we just hooked up an op-amp. And we can use this to boost voltages, basically the difference of these two voltages on the inverting input and the non-inverting. So the non-inverting input is the positive terminal here. I like to just draw op-amps as a box, but for fun I can show you what's inside of an op-amp. They tend to look like this. Pretty nasty. If you're just starting out with electronics, but these are different stages, and not every transistor is an amplifier. Maybe some of it is a current mirror or resistance or whatnot. But it's these different transistor stages that make up an op-amp. But we don't have to talk about that right now. We'll just look at it as a black box. And as I showed, if you take 100 millivolts and 0 volts, the output is just going to saturate to whatever VCC supply you connected it to. So that's not very useful. I guess you could turn that into a comparator. For example, so the op-amp can saturate to the positive supply and to the negative supply. So if whatever's on this terminal is higher than whatever's on this terminal, so for example, I do 120 millivolts here, 100 on the non-inverting input, then the difference is going to be 20 millivolts, but negative 20 millivolts. And so that's going to saturate at negative 15. So that's your negative supply. So you can use that as kind of a comparator. If this voltage is higher than this one, then it's going to go high. It's going to saturate at the positive supply. And what that would look like, maybe do, oh, what a terrible, 3.3 volts on the positive VCC supply, and on the negative VCC supply, you go ground. Now you have some kind of comparator. So this is going to give you low. It's going to saturate at ground, or whatever is the negative VCC. And let's say this is 200. So now this one's higher than this one. It's going to saturate at 3.3. So now you have kind of a comparator, but it's not a good comparator. If you have multiple op-amps in the same package, and one has saturated, the other op-amps tend to not work as well. So there are other comparator ICs or circuits that are more suited to be comparators. So that's a tough word to say. So what's the purpose of an op-amp then? Well, we can control gain with it if we do a connection that looks like that. So let's derive the transfer function for this op-amp configuration. That is important is when we have negative feedback, then the op-amp is trying to drive these two inputs to be equal to each other. So we can, so if we have negative feedback, then this equation, we can use this equation. So the voltage on our V plus terminal is V in. So I just replace that here. And since there's no current that goes in here, we can just use a simple voltage divider from this point to this point. So let's rename these to R1, R2. And let's just use the voltage divider. And now to find our transfer function, which if you recall is just our V out over V in, we just have to do some algebra. So we can multiply this denominator to this side. And now we can divide by V in on both sides and divide by R2. So we get here we go, and we can separate these two into two fractions. And these two are just gonna be 1. So this is now our transfer function. And as you can see, we can now control the gain. Let's say we put in 100 millivolts. And we size our resistors to be 1K and 1K. So these are going to be cancel out or be 1 plus 1. So it's going to be 2. So we now can control our gain with this. So if we size this one to 1 kilo ohms, then if we put whatever we put here, we're going to get twice as much. Up to, let's say, 15 volts. Plus or minus. Keep in mind that the op-amp cannot provide a higher voltage than the supply voltage. So if you put in 10 volts as your V in times 2, that's 20. So that just means it's going to saturate here. It's not going to reach the 20 volts here. If you wanted 20 volts, you would have to put a 20 volts on your supply here. Now the cool thing about this is if our gain is 2, then we can create a block diagram out of this, right? These two are equivalent. So we can just remember, if you can learn to remember this op-amp circuit, then you can start building block diagrams. And we're going to do more complex block diagrams and convert those into op-amp circuits or just any other transfer function. So the cool thing about block diagrams too is so you have this, each line here is a signal, and each block is a system or gain. And you can find the transfer function of any block by just taking this signal here, dividing it by this one. So in this case it's just V out or V in. But you might have a block diagram that looks like that. Let's just call this V1 and this one V out. Which would mean that if you wanted the transfer function of let's say this block, you would do V1 over V in is equal to 2. Or if you wanted the transfer function here, you would go V out divided by V1 is equal to 8. And the cool thing is, as you can see, to find the transfer function of this one and this one, we just multiply these two together. Do V1 so when you have two blocks like this, it's called having two blocks in series. And it's as if you just multiply through. So let's convert this into a op-amp circuit. So we have our V in, and it goes into the first gain of 2. And let's just size them to 1K. We already know that's going to be a gain of 2, according to this formula. Or you can do 10K, because they'll still just turn into 1, as long as they're the same. And then we just cascade it, or we put them in series. So whatever signal comes out here, we'll call that V1. God, I can't draw. Here we go. And we need the gain of 8, so let's do 7K, 1K. So that's going to be 7K over 1K, 7 plus 1, 8. So we just implemented this block diagram electrically here. So we should get 16 times our input. So if we do 100 millivolts times 16, what's that, 1.6 volts? So that's controlled gain. And this op-amp circuit is called a non-inverting op-amp circuit. And we can cascade them or put them in series, and we can build block diagrams that represent this non-inverting op-amp circuit.